8.2, number 20. Uh, let's look at that. Can you hear me all right?
Mm-hmm.
Yes.
Oh, I remember that one. So I'm actually gonna, so wait, when is this due? Is this due,
Monday.
it's due on Monday?
Yeah.
I actually have, I actually wrote up some stuff about that one.
Oh, okay.
Okay.
Because I just want to make sure I had it right. In fact, let me see. Hold it. I don't think that you can actually do this. You can count this one precisely.
Yeah, it said approximate. I think
Yeah.
approximate.
Okay. So yeah, it did say that. Yeah. Okay. So this one's crazy. I mean, I almost believe it when I did it. So let's see if I can. I'm looking for where I wrote this. Hang on a sec. Give me a second. Here we go. Can you still see me?
Yes.
Mm-hmm.
Here, I'm actually, I mean, there's no, I mean, I'll basically end up kind of showing people this anyways, but this is what
Do you want us to wait? Would that
no,
be
it's
easier?
okay.
Okay.
But this is just a way for you to think about it. So can you see this?
Yes.
So we're imagining the cards being labeled like n minus 1 all the way down to 1 from top to bottom. That's how I'm kind of thinking about it in my mind.
So N is on top?
Yeah, I'm thinking about it as with n on top. I don't know, is that how you were thinking about it, Elise?
I think I was thinking about it with 1 on top, but I really wasn't sure what I was doing. So either way.
I honestly don't think it matters so long as
Yeah.
it's consistent. So I said, let's just let U be the universe of all possible drawing sequences for each I, and AI is just the collection of sequences where the card labeled I is on top at some point. Okay.
Okay.
So that's kind of how I defined my A. Does that kind of make sense?
Mm-hmm.
Yeah.
So AI is the collection of drawing sequences where the card labeled I is on top at some point. Because aren't we like we're drawing like random numbers or something, aren't we? Or
Yes.
we're basically taking it, and so you're kind of going down into the deck, and you know, if card, so AI is the collection of sequences where the card labeled I is on top at some point. If the chosen card number, okay, so right, it's a successively pick a different random number between 1 and n and remove all cards in the pile down to and including the card with this number until the pile is empty. Okay, so so I'm letting AI just be the collection of sequences where the card with label I is on top. And then like I used inclusion exclusion. Do you see this right here?
Mm-hmm.
Yeah.
See this right here? I mean, that formula is just basically the formula for exclusion, right? For probability, at least. And then I was telling myself, you know, what's the size of the universe? You know, what's the collection of all drawing sequences? And I'm gonna tell you right now, think about this. See this formula right here? This is n-1 put I. Does that make sense? Where is this coming from? I'm counting the number of drawing sequences right now, okay? And I am telling you the number of drawing sequences is this sum right here. Eventually, if I'm drawing random numbers, I'm going to end up just evaporating the whole pile. Do you know what I mean? I'm just going to end up the whole gone. And I'm telling you, if you think about it, this sum of these permutation numbers is the size of the universe. And incidentally, the approximation comes from this. It comes from using the power series for the exponential function. Okay? So it comes from using the power series for the exponential function. But I'm probably going to send out a couple of hints, maybe like tomorrow or something on that one, because that one was definitely the hardest problem for sure.
Okay.
But hopefully, like AI being the number of drawing sequences where the card with label I is on top, that's relevant to this problem, right? The way that the problem is laid out.
Yeah.
Yeah. And using inclusion-exclusion that way, counting the number of things in the universe by itself kind of reveals how to do the problem. Okay, so here's this right here. And then this power series for the exponential function. Those are kind of the three major components. And so you, like, you know, the number E is approximately, you know, this thing evaluated at 1 and truncated at some point. I think I end up using that below somewhere. Okay. But those are the three core components. Is that at least a place where you can kind of start working from?
I think I'm having a hard time understanding how we're getting the size of the universe.
Okay. So, all right. So, let's look at this. So what U is just the collection of all possible drawing sequences, correct?
Mm-hmm.
For this thing. And what is it that we're doing? Cards, I'm thinking of the cards numbered 1 through N, just like in order, 1 on bottom, N on top. That's the way I'm thinking about it. And again, I don't think that the computation would be different if you switch the order. I think it would be. So, and then what are we doing? We pick a random number between 1 and N, and we remove all the cards in the pile down to and including the card with this number until the pile is empty. Okay. So basically, I pick a random number between 1 and N and remove all cards down to the pile down to and including the card with the number until the pile is empty. If the chosen card number has already been removed, we pick another number. Yes.
Mm-hmm.
In some ways, it might actually be easier if it was 1 to N, like if 1 was on top. I mean, just so that you don't have to flip things around in your mind. You know what I'm saying? So maybe if we go 1 down to N, we choose a random number. So if I chose the number 5, what would I do?
Remove cards into. Oh.
What's that?
If it's from 1 to N, then remove the first 5 cards.
Yeah, you would just remove the first 5 cards down to that one. Yeah, that's right. And then, and it says if the chosen card number, so I'm going to pick another number. Okay, so that is like if I picked the number 3 next. So suppose I picked 5 first, yes?
Mm-hmm.
Okay, if you want to think of it 1, 2, 3, 4, 5, you would go all the way down to number 5. You would remove it. So the card on top would be 6 at that point. Yes.
Mm-hmm.
Number 6. Mm-hmm. If the next number I drew was 3, I would say, well, forget that. You would throw that away. and then you would keep picking until you picked a card with the particular numbers that are left down there, and you would remove cards down to that one. Does that make sense? Like the process itself, at least?
Yes, yes.
Okay. What is the approximate probability that at some stage the number chosen is the card on top of the pile? So for instance, in that example where we said, you know, we picked 5 first, yes?
Mm-hmm.
We picked 5 first. Well, so if we were going to pick the card on top, we're going to pick the number whose card is on top at that juncture. What number would we have to pick next?
So after doing the 5, then it would
Yeah.
be 6.
Yeah, it would have to be 6. Does that
Yes.
it would have to be 6? So that's what we're wanting to know. We're wanting to know at what point do I end up, or like, what's the probability that at some point I end up drawing the number of the card that is on top? So basically, that would mean that you would just pick that card that happens to be on top. That's what's going on. They just want to know when does that happen, or how often is it that you at some point are just basically taking the top card. Okay. And actually, I'm going to kind of give away. I think I'm going to let you think about this.
Okay.
This is true. The number of drawing sequences is this,
Mm-hmm.
but I'm also going to say I'm going to give away the farm. The probability that you draw the number in at the very moment that the bottom card is the only one left, almost always happens. That's going to happen with like almost 100% probability.
Okay.
Does that make sense? So
I
the
think so.
answer to the problem is actually fairly close to 100%.
Okay.
It almost happens 100% of the time. So I'm just going to say like this sum right here, it's too, showing that the size of the universe is this is too beautiful for me to like, for me to just tell you exactly why that's the answer to the size of the universe. It's not hard. I promise it's not. Just think about why the total number of drawing sequences is given by this sum. So I'm going to let you think about it, because I have several days to think about it, and I'm giving you some more hints.
Okay. Thank you.
But I know that one was the hardest one, no doubt.
Okay.
Did you have any other questions?
Yeah, I think we wanted to talk about 25 next. I have an answer for part A, but I mean, I don't know if it's right, and then exactly how to see if it's the same as the equivalence relation. I'm not sure how to start that.
Yeah, me either.
Show that your answer equals dn plus dn minus 1. Okay, so what did you do for part A?
What?
What
Sorry.
did you do for part A? Can you explain to me what you did for part A?
So I just tried, I just pulled out a few S's to try, and I came up with a pattern that had n factorial out front, plus the sum from k equals 1 to n minus 1 of -1 to the k times n minus 1 choose k times n minus k factorial.
Okay. Interesting. Okay, how many arrangements, right? So I is never immediately followed by I plus 1, or I is never immediately followed by I plus 1. So that's that's not too hard. What you do is you count the number where that does happen, yeah?
Mm-hmm.
So, and that's like those two things being glued together or something.
Yeah.
Right? So So tell me, so can you explain to me how you actually counted those things? So what were your sets? So what was, so it was like
So,
A1?
so A1 would be the arrangement where 1 is followed by 1 plus 1 or 2.
Right, so that you see 1, 2 somewhere, right?
Yeah.
Okay, and then A2, you would
You
2,
would see
3
2, 3
somewhere.
somewhere.
Yep, yep.
Okay. So AI would be, you'd see 1 followed by I plus 1 somewhere.
You would see I followed by a +1. Yeah,
I plus 1, yeah.
okay. All right, and you know how to count each one of those, yeah?
Yes.
So the size of like AI is just n minus 1 factorial, basically.
Yes.
Okay, what's the size of like, okay, so what's the size of like AI intersected with AJ, for instance?
I said it was
10?
2 factorial.
You did, so say that again?
N minus 2 factorial, because you'd glue 2 numbers to 2 other numbers, so you'd have 2 sets of 2 numbers. So you'd be 2 less numbers than you had.
Well, but that's if those things overlap one another. So that's, you're right that the size of A1 and A2 would be n minus 2 factorial. But what about the size of A1 and A3?
That would still be n minus 2 factorial, wouldn't it?
Would it? Because
Yeah.
how could you explain that, Elise?
Because then you have, I guess, 2 groups of 2 that you're kind of squishing
Okay.
together. And then, yeah, you get rid of.
Yes. Okay, so that's still n minus 2 factorial. Okay, so I think that we're okay there. Okay, what about A1, or what about AI, AJ, AK?
I had n minus 3 factorial.
Okay, are we sure about that? There's several cases.
Yeah.
If you have 3 groups of non-overlapping 2s, then we still lose 3 letters, yeah? Or 3
Yes.
letters. If we have if we have 3 letters over, if we have an increase of size 3, that's still losing 2 letters, and then we still lose 1 letter from the other group of 2, yeah?
Mm-hmm.
So it seems like every time we're losing 3.
Yeah.
That makes sense?
Mhm.
Okay. All right. So I think that we can say with fair confidence, that the number of these things, so you said it was like n factorial, right?
Yes.
Yes. Is it n minus 1 times n minus 1 factorial
Yes.
Mhm.
plus n choose 2?
N minus 1 choose 2.
Oh, yeah. N minus 2, okay, and the first one's really n minus 1 choose 1, if you think about it for a second, yeah?
Mm-hmm.
Then it's like n minus 2 factorial minus ... right? But what is that? Isn't that just like n factorial minus so okay. So is there a simplification that happens here?
Well, I had the summation negative 1 to the k, n minus 1 choose k times n minus k factorial.
Right, n minus k factorial, but the n minus k factorial like cancels, doesn't it?
Oh.
Or does it? Well, almost. It almost cancels.
Yeah.
What's left?
Well, it wouldn't cancel on S1.
Right. So, well, it doesn't really cancel on the other one either, but almost everything goes away except one thing. I mean, do you see what I'm saying? Like the denominator of n minus 1 choose 2, for instance,
Mm-hmm.
factorial times n minus 3 factorial.
Oh, yeah.
Do you see what I mean?
Yeah.
So this is like n minus 1 factorial over 1 factorial. I'm doing the S1 thing. And then it would be n minus 2 factorial. So that's just like times n minus 1, right?
Mm-hmm.
N minus 2 factorial cancels everything except the factor n minus 1. What would the third summand be? N minus 1 factorial over
3 factorial.
Over 2 factorial times n minus 3 factorial. But what happens to the n minus 3 factorial?
It'll go away.
And you're just left with like n minus 2. Do you see?
Mm.
Do you see what I mean?
Yeah.
And then like the third one is going to be n minus 1 factorial over what?
N minus 2 factorial.
So I'm doing the S3 case right now. So minus n minus 1 factorial over 3 factorial, n minus 4 factorial, but that can't everything except the n minus 3. Does that make sense?
Mm-hmm.
And you can kind of see how this is going to go. Now, don't we have formulas for dn plus dn minus 1? Don't we have formulas for that? For dn, don't we? I think we did that in class, but we also, right, so if you look at the bottom of page 333, there's a formula for dn. Okay?
Okay. Okay.
You see it?
Mm-hmm.
My suggestion, okay, and this is my suggestion, and believe me, it will work. Okay, I mean, I'm looking at it right now. Okay, just take the formula for dn and take the formula for dn minus 1 and add them together, and just like put like terms together.
Okay.
Does that make sense? And show that it equals this formula that you just wrote down. I'm telling you, the algebra is going to be such that it will work out.
Okay.
If you have trouble on that, you can ask. I mean, again, I'll be in here. We'll have class today, right?
Yes.
Mm-hmm.
You can come ask in class, but there's just a little algebraic maneuver that you have to do to get that to work out.
Okay.
All right.
What else?
Do you have one of these?
Let me look. Do you have one ready?
Well, I kind of want to talk about 23. I mean, I know we talked about like how to do it last week when we did part B, but I tried to do part A the same way and I did not get the right answer. So maybe I just don't understand what's going on well enough.
How did you try to do it? With inclusion, exclusion, or did you just try to do it directly?
Well, I tried it both ways and neither answer was right.
Well, okay, so you have to be careful if you try to do it the Ilona Weeble way.
Okay.
Yeah, because you're going to have to split it up into a couple of cases. So, well, if I have in colors, so what if you, well, here, I'll go like this. Watch this. Watch this. So like this. So, oh my word. Look at this disaster. Okay.
Okay.
How many options? Let's start up here at the top. How many options do I have for this guy right here?
N.
Okay, and then how many options would I have here?
N minus 1.
Yeah, that's right. And n minus 1 here.
Yes.
Okay. So what about this?
N minus 1.
Yeah, no, but here's the thing. I'm going to put a little asterisk next to this. Here's the thing. The number of choices for this one
Mm-hmm.
depends on whether these two guys are what?
The same or not.
Yes. Are they the same or are they not? Yeah. So guess what? That's going to mean you're going to have how many cases?
2.
Yeah. So if they're the same though, that's going to change this factor.
Mm-hmm.
Like this factor would no longer be n minus 1. Do you know what I'm saying?
Yeah.
So really what you want to do is think of this as either 1 or n minus 2. I mean, this is this is the case where it's the same, right?
Mm-hmm.
And what's the n minus 2 case?
Where it's different.
Yeah. Does that make sense?
Yes.
Is that what you did or did you?
That's not how I did it.
Okay. You could do it that way. You could also do it
Okay.
using inclusion exclusion, but that's the easy way to do it. We're going to split
Okay.
it into just 2 cases and pull it off.
Yeah. Yeah.
Is the Ilona Weeble way. Yeah.
Anything to make it shorter.
But you can do it using inclusion exclusion, no question.
Okay. Yeah.
That makes sense, hopefully.
Yes. So could you also do a similar argument for part C? Because like I noticed in this one, we have 7 edges for 5 vertices. And so that makes the inclusion exclusion more intense.
Yeah. You can, yeah, I might try to do it the simple way.
Okay.
It will make it more intense. You'll have 7 sets.
Yeah.
You can handle it both ways, but actually the graph is, so there's some nice symmetry going on. I mean,
Mm-hmm.
you have the 2 degree 2 vertices,
Yeah.
2 degree 3 vertices, and you have the 1 degree 4 vertex. So it is possible to kind of to systematize the inclusion exclusion thing.
Okay.
I think you can actually do what I just did in the last case.
Okay.
I think that you can do that, but you're going to have to think about, at what point does my choice start to depend on what's going on? Know what I'm saying?
Yeah. Yeah.
So,
Okay.
you guys doing all right?
Mm-hmm.
I think so.
Yeah.
So, yeah. Did you guys see the lecture for today?
Yes.
Yes. Yeah.
Does that make sense?
Mm-hmm.
Yes.
Good. Yeah. Chapter 9 is going to be interesting. No doubt about it.
Interesting or interesting hard?
I don't think it's like that hard necessarily, but it's just fun. It
Okay.
seems like you shouldn't be able to do what we're going to be able to do.
Okay.
Okay.
Yeah. All
I
right.
definitely really enjoyed the rook polynomial stuff and 8.3.
Yeah, that's super powerful, isn't it? Man.
Mhm.
Well, guys have anything else? I mean, of course, you can come in and ask more questions during the afternoon,
Yeah.
and I'll be more, I want you to kind of have to think through a couple of things, but I'll definitely give you some more hints if things aren't making sense since then.
Okay.
Okay.
Anything else?
I think that's all I had for now, but I might have more later.
All right, cool.
Yeah.
Awesome.
I-
Thank you, Dr. Hammett.
Yeah,
I
yeah.
am actually interested in talking about 27. I worked on it and got lost, and then I looked at the answer in the back of the book, and that just made me more lost. Yeah.
Here, if two identical die are rolled in successive times, how many sequences of outcomes contain all doubles?
So I did my A sub i's to be sequences where the ith roll isn't a pair.
Isn't a double.
Yeah, isn't a double.
Yes.
Um,
That's how you should do it. Yeah, I think so.
okay. And then
The ith roll is a double. Yes.
yeah. So the universe would be you'd have to choose a number for each pair. Or no, you choose the universe would be where you would choose a number for each die for each roll.
Yeah, so it's going to be 36 to the n.
Okay.
That's the size of the universe.
Okay. So
Total number of the total number of sequences of n rolls. The total number of sequences of n rolls of pairs of die.
yes. So then for A sub 1, where the ith roll isn't a pair, I had 6 choose 1 times 5 choose 1 to pick two different numbers for the first roll. And then, but then it would be times 36 to the n minus 1.
So AI is the number of roll sequences where the ith roll is not a double.
Yes.
And so you have n sets, right?
Yes.
And so it's pretty clear that the sizes of those are all going to be the same. Yeah. So you're going to have like 36 to the n minus, okay, n choose
1
times. So, okay, so go ahead.
n choose 1 times 6 choose 1 5 choose 1
Times 6 5. Why do you have 6 5?
Well, because you don't want it to be a pair. So you have to choose.
AI is the number of sequences where you have. I thought you said that you actually have a pair on the ith roll.
Well, I defined it where the ith roll isn't a pair so that I could use the formula for not A1 and not A2 and
right, so you don't want it to be right. So the
yeah.
identical sequence outcomes contain all doubles. Oh, contain all doubles. If two identical die are rolled in succession, how many sequences of outcomes contain all doubles? Oh. I think what that means, Ellie, is that you see a pair of ones somewhere, you see a pair of twos somewhere, you see a pair of threes somewhere.
Oh.
You see a pair of fours somewhere, you see a pair of fives somewhere, you see a pair of sixes somewhere.
Okay. Okay, so it's not like every roll is a double.
Yeah.
Okay.
So I think you should only have 6 sets. So like what should the first set be? A1.
A1 should be the sequence where you don't have a pair of ones.
Where you don't have a pair of ones. That's exactly right. So there's only 6 things here. Does that make sense?
Yes.
So then you're going to have A1, not A1, and not A2, and not A3, and not A4, and not A5. And that's a lot easier than what we were just trying to do.
Yes.
Jeez.
Uh,
So like not A1, so that means you don't see a pair of ones somewhere, right?
yes.
Well, what's the size of A1?
So A1 would be, it's already chosen for you. So then it would be, you'd have 5 options for every, no, you'd still have 6 options. You just couldn't have 2 ones together.
Yeah, that's right. So that means that instead of, you would never have the option of rolling 1-1,
Yes.
a pair of ones. So that means all the other options are okay.
Mm-hmm.
Just be 35 to the end.
Oh, yeah.
Is that right?
Yes.
What about it, the size of A1 and A2?
So that's where you could roll no pair of ones and no pair of twos. That'd be 34 to the end.
That's exactly right, yes. Is that sounding more like what's in the back of the book?
I think so. I think that some could come out too.
Yeah.
Okay. Yeah, I think, yeah, I'm sure if I could have just interpreted the question differently, I would have been able to figure it out.
Yeah. Sorry. I mean, I got sucked in too, so.
Well, that's
I was
the way
like,
I
there's no way
explained
this.
it.
What's that?
That's the way I explained it.
Right. So I got sucked into that and I thought, man, I don't remember having to do one that hard. Yeah. There you go.
Okay.
So the hardest problem is number 20.
Okay.
I'm just telling you guys that right now.
All right. So if anything gets harder, I just need to reread the question.
Yeah, that's right. All right. So, hey, come with more questions at whatever time that is.
Okay.
Okay.
Yeah.
I probably will.
Yeah. Cool.
All right. Thank you, Dr. Hammett.
Thank you.
Yeah. Thank you. See you guys later.
See you later. Have a good day.